Okay, we start again. This afternoon we have two seminars, so we start the second session, and we have now Enzo Marinari, who is very well known by everyone here, and is perhaps is one of the closest collaborators of Giorgio, since ever one of the closest friend. And it's also nice because he's one of those who witnessed the transition from the high energy lattice QCD part of the Giorgio career to statistical mechanics. So witnessed the transition from the previous talk to statistical mechanics. And in fact, he will talk about simulated tempering. So Enzo.
Okay, thank you very much, Giacomo. Thank you to all of you. And indeed, I want to start by thanking the organizers, mainly the young organizers say, this has been a great idea. And I think we have found an opportunity that is really worth, and I think something is gonna stay from these talks that will, clarify many things. As you see from my title, I've been a bit carried away. Right? I'm supposed to talk about simulated tempering, but by following Mrs. Rowling, I've added a number of fantastic beasts. Indeed, also there, I've been lucky because Maria Paola has been talking about one of my beasts. I didn't have that in the talk, the smearing, right? But I think it has done part of my point and will be useful in what we discuss together. The point being, say, the passion of Giorgio for algorithms, I will come back to that. And now a kind of consistent picture that contains a lot of knowledge, indeed, has come out of that. So simulated tempering, I have been lucky enough to be an author of that with Giorgio, couples with many other fantastic beasts. And if I will have some time, I will tell you something about that. Also, I want to say right that I'm very happy that Giovanni Ceccotti is here, because we will see during this exposition that the tradition that in some sense now Giovanni represents is very present in what I'm going to tell you, and has been very important for this kind of developments. So I don't know if that works, probably not, so I will just now it works. Okay, it was blocked. So let me give you a little bit of a summary. So simulated tempering is indeed an optimized Monte Carlo method. The basis of a follow-up that I will discuss. So first I will introduce you a bit Monte Carlo methods, because I think this is useful in any case. And you see, I will try, in all what I will do, somehow it will be a framework that will include, in general, statistical mechanics, say of discrete, of lattice variable, I would say. So lattice grid theory and magnetization, Ising model, and eventually spin glasses, they all fit in this framework. So I will try to be very general, okay? And to give you an idea, you will see many of these developments are start from 81, 82. So this is mainly lattice gauge theories indeed, but this is statistical mechanics. And as I told, Giovanni will show up to be important in that. And simulated tempering is from 92. So Monte Carlo methods. And I will tell you something about systems with multiple equilibria, that is what has led Giorgio to Nobel Prize at the end. And why systems with multiple equilibrium do need a very severe computational effort in order to be understood numerically, because multiple equilibrium means that there are barriers among the different stable states of the system. But we will see that. And so then I will go to what I have to do, because I'm paid for that, simulated tempering, that I will discuss, paper from 92, and parallel tempering. And then I will use that to give you a few feelings about temperature chaos, that is an important effect in complex systems. And that indeed can hamper for very large lattice size the performance of these optimized numerical methods. And then if I will have time, I will have the two other fantastic beasts now basically being reweighting, that is the possibility of computing expectation values from a Monte Carlo run for different values of the temperature where you run it, and specifically also for complex value of the temperature. Since we know, I will come back to that phase transitions are a problem of complex zeros of the partition function that collapse on the real axis of the temperature, we will see that dominating that. So this has been another Giorgio idea, a paper in collaboration with a few others. And then also, if I have time, I will tell you something about large distance correlation functions. That is how, with Langevin equation, you can control the large distance behavior of correlation function by being precise in your measurement. Okay, so first point is inventing good algorithms basically means using in designing them all what you know about the problem. So somehow, if you know something about the problem and you can put it in, then you will probably, if you do it carefully, if you do it cleverly, right, lead you to a performing algorithm. So again, I mean, from also from the study I've redone of literature, Giorgio has surely always been very passionate for algorithms. And you find so many of them in his scientific production that there is no way, I mean, to discuss all of them. The APE compiler is indeed one example, because the compiler was an algorithm that when, you know, when it was decided in this department to build this parallel computer, basically there were two influences that were very strong. One was Nicola Cabibbo, that was completely in love with hardware. He was a good friend of Toffoli at MIT, and he was playing with a little television on which he was implementing cellular automata. And then there was Giorgio. And Giorgio was passionate with algorithms. So, for example, with compilers. And so Nicola said, but maybe I can give ideas about how to build an hardware, right? Very powerful. Giorgio said, yes, but also I can suggest how to build a compiler and an optimizer that will be very powerful. That is what they did, that is what we did, that led to a big Italian success. And I will never forget when Giorgio came with a book. It was a wonderful book with a big dragon on the cover. And there was some horse rider, right? Cavaliere, that probably killed the dragon. I don't know, right? But that was, you can win against the dragon with your wonderful compiler. And this book was a book of compiler theory, and indeed it has been the basis of what eventually was developed, right? So here I will discuss numerical simulation and Monte Carlo methods, and we leave aside many of other Giorgio developments. I don't know, optimization theory, good pseudo-random numbers. Just I have an observation that I want to do, but in some sense, I believe that now, when Giorgio worked out Parisi theory and replica symmetry breaking, that was very algorithmic in his mind. I mean, because the first, as you know, or more of you, when Giorgio wrote his theory, the physical interpretation of the theory was not clear. And so Giorgio wrote it on the basis of first principle. I mean, he wrote down something that maybe could work. And that was algorithmic, I believe, and then it worked. And then it was even the correct mathematical solution of the problem. So it was, but you need also a little bit of luck, right? To be very successful in life. But I mean, it was a very powerful idea that came on the basis of building something in some sense, algorithm. You see, I write here, a consistent step-by-step procedure that brings you to the result. So I claim to bring, say, also replica symmetry breaking in the field of a fantastic algorithm. So let us put it also as a fantastic beast. So let me start a bit about Monte Carlo methods. Right? Monte Carlo methods are of primary importance. A random integration, they scale well, say, when you go to very high dimensionality. You want to integrate a very complex manifold, and somehow you can do it with a random procedure. And when the dimensionality, say, of your system is high enough, then it turns out to be the best way to do it. We have to notice that indeed there are two different basic meanings of the procedure. And we should not confuse them together. On the contrary, we should distinguish them. You can use Monte Carlo. I remember discussing that with you a few times. You can use Monte Carlo to reproduce the dynamical behavior of a physical system. Clearly, that would be molecular dynamics, the right way to do it. But you know that if you use for Monte Carlo a simple enough kind of dynamics, you find the same asymptotic behavior of the dynamics that you would have for the physical real dynamics. So, say the critical exponents in some sense, if you want, but in any case, clearly, in order to do that, you have to get a dynamics that is very similar to a physical dynamics, meaning local dynamics, local in space, local in time, etc. So, in some sense, not very effective. I cannot do a physical dynamics by saying that an atom get information for an atom in the other room right away, right? That do not work. The different component of a crystal speak with elements that are close to them. So this is dynamics, Monte Carlo for reproducing physical dynamics. And this is important also because in many situations, we are understanding now that you really don't go very close to equilibrium, to Boltzmann equilibrium, in statistical mechanics of complex systems. So dynamics is very important. But there is one other important meaning of Monte Carlo. That is, if you look at Monte Carlo as a tool to sample the equilibrium probability distribution. So I have E2 minus beta H, Boltzmann distribution, statistical mechanics. So I want to sample this distribution, where this Hamiltonian is a function of the configuration of the system, of the degrees of freedom, right? And you want to sample it fairly. At this point, you have no need whatsoever to stick to a dynamics that is a good approximation of a physical dynamics. You don't need to stick to dynamics that is local. You can be as smart as you like and as much as you can be. This is, by the way, an old idea. I will quote that by Torre and Vallot from the 70s, density umbrella scaling, and so on. You can change the dynamics and use a different probability distribution compared to one you would use for simulating the physical dynamics, if your goal is only to sample the probability distribution. This clearly is also valid for lattice gauge theory, right? Hybrid Monte Carlo, over relaxing. I mean, you are just trying to get a sampling of the probability distribution. So, Monte Carlo, let me define for you, for example, a local simple approach in really 30 seconds, but as we said, is okay for getting the main feature of physical dynamics. So for example, Metropolis algorithm, this is very nice because you can do it even if you know nothing about the system. Indeed, Metropolis did it for neutrons in a situation when everything was very complicated. You just to be able to compute the Hamiltonian, but you don't need to compute anything detailed. So you select a variable, maybe a random. You propose to change it. For example, a spin, you propose to flip. You compute the change in energy induced by this change. Now, if the change of energy is negative, so the energy diminishes. Very good. You're going to the ground state. This is something you want to accept. If you do only that, you would just do what is called steep descent. You would end up in a local minimum. But in metropolis, what you do is that, oh, this is larger than, I apologize. But if delta is larger than 0, you accept the change with probability e2 minus beta delta. Now, if you go and check, you see that this satisfied balance, and indeed samples Boltzmann equilibrium distribution that I've written here. So this is a good, simple method that we can use. Now, let us think at simple Ising model. Spins that are plus or minus 1, ferromagnetic interaction with the first neighbors, right? Something very simple. And for example, now, if you have large temperatures, it's very easy to obtain reliable results for expectation values of energy, for example, from simple Monte Carlo. This is because there are no high energy barriers. But I want you to notice that already when you go in the broken phase of the Ising model, the situation is a bit more complicated than what you would think. Because you see, so look at that. Don't look at this one. This is Parisi. It's complicated. We look at it in next slide. But so this is typically free energy versus magnetization. Okay, high temperature is just a parabolic behavior close to m equals 0, and clearly doing Monte Carlo is pretty easy. But as soon as you go in the broken phase, already you get a phase transition. Right? What does it mean, a phase transition? It means that you have two possible stable states of the system, right? And that this barrier is an infinite barrier. So when you start your Monte Carlo, typically, you just study half of the possible phase space, okay? But you say, fine, there is a symmetry. So you know exactly what happens in the other half space. So you don't do well the Monte Carlo when you are in a broken phase of an Ising model, but you don't care because you know the results in the other part, okay? So, so numerically, for this model VNTC in visual Ising model, you only study half of the configuration space and use what we know about the symmetry to claim, because it's true, that we know also about the other half. And now this is the same picture of before. Typically, this is a Parisi picture, right? Lot of barrier, multiple equilibrium, right? So there are many stable states or even very, very slow decay metastable state. Okay. This picture should be in 10 to the 23 dimension because we don't have the presence of a magnetization, right? And so we should look at it. So in this case, right, we have barriers, infinite barriers in the infinite volume limit that separate states that don't have an easy and direct symmetric relation with the other states. So we cannot use our little trick of Ising model. We do one state and we are done with everything. Here, we have to do it all, okay? And so this is the problem. If we want to study a system of this kind, and I can be very general at this point, a system with multiple states, by Monte Carlo, I need the Monte Carlo method that would allow me, during the dynamics, to pass these barriers that are indeed very high, infinite, in the infinite volume limit. Okay, clearly already finding ground states is very difficult. Annealing works, annealing helps. What is annealing? You start from high temperature, okay? And then you start to decrease the temperature very slowly, okay? And then you record the low energy states that you find. The problem is that obviously with this procedure, when you sit a finite temperature, you are not at thermal equilibrium. So what you are doing is useful, and already that you can do it is a kind of gift. I will comment in a moment about it. It's useful for finding the ground state, but is not for analyzing the final temperature equilibrium property of the system. It is non-trivial that annealing even could work for finding ground state. The problem is that in bona fide regular complex systems, there are some that don't do that. Deep basins are also very large. And so this helps us, because if you have a system, the one we kind of call golf course-like, etc., this would not work. But in many situations, we are used to this kind of work. So it's clear that in this situation, Monte Carlo is very difficult. The standard approach does not work, and you get stuck in local minima. So the idea is, can you change this was called, for example, first umbrella density approach? In some sense, simulated tempering is a variant of umbrella density approach by Torri and Vallot in 77. And then I will show more references. At the end of that, I will show you some 10 very relevant reference. Okay. So the idea is, as I told you before, since you don't care about the dynamics, but you only care that this dynamics is sampling in a fair way the equilibrium Boltzmann distribution, you can change the dynamic transition probabilities. In some way, you believe is clever, okay? You lose the relation to physical dynamics, but you can be far more effective. Simulated tempering that was proposed in 92 can be seen as an annealing. Just remember these words, and then they will be explained in the following, where an annealing where the system is always at equilibrium, even when you change its temperature. Now I will give you the formulas for seeing that. And here we go, and I can discuss for you simulated tempering. I can promise now that in 10 minutes time, I will show something even more very simpler, that is parallel tempering, and where the kind of fine-tuning you have to do is really smaller. So rough space makes numerical simulation very, very difficult, okay? And so that's what we did with Giorgio. First step, enlarge the configuration space. What you do, you say the following. Now, not only the spins, your degrees of freedom, the plaquet, the gauge fields, the spin, what you want, are degrees of freedom, but also the temperature becomes a degree of freedom. So I tell you, I define a new Hamiltonian that is function of the fields of your theory and of the inverse temperature. The inverse temperature is now a variable. And this is beta m h minus a constant that we'll see, where beta m can now take m different values. Selecting these values will be our goal and say the important thing to do. So the new enlarged probability distribution is now, I've included now beta in H. I hope, if not, consider it is included. P temperature, and also probably I have put a minus signs, but I mean, this is okay. Exponential of this new Hamiltonian. So what we must do? We must select both the number of this value of the temperature and their values. And also, you see, I have another thing I have to fix, that is the set of this constant Gm. I will give you, in a few moments, the physical important point in order to define that. And also, we get rid eventually of this G of M, okay? So, the beta M are now dynamical variables that can take values among a set of values we allow, while these Gm are constant we assign a priori, But in this approach have to be fine-tuned. Okay, parallel tempering, also called replical exchange, that I will discuss with you in a few minutes. That is an evolution of simulated tempering, if you want, takes care about that and simplifies very much the procedure and minimizes the need for fine-tuning, meaning getting rid of this GM. Let us assume that these beta are ordered, okay? And let notice that the tempering probability distribution, where restricted to subspace of fixed M, is the usual Gibbs distribution for beta equal beta M, right? Because there is any beta M, I fix it, and then in this subspace, this is fixed to be Boltzmann at this beta. Also, if I look at a given value of M, okay, and I look for the probability of finding this value of beta, then in this case I have to integrate over the sigma, and then I find that I will have basically PM will be the partition function at this value of M times E to GM. So E2 minus beta M Fm is the free energy density plus GM, where zeta M is the integral over all the sigma, because I'm doing a restriction to a given value of beta M, okay, of this extended partition function. Clearly, you see from this expression that if we would be able to set GM equal basically F of M, the free energy density for all values of M, then all the probabilities PM would be equal, and the method would work like charm. Problem is that we don't know the value of F of M. Again, try to bear with me, because I will give you in a few moments a very simple receipt. So we don't know the F of M, we need a good value for the G of M. And also, I need to select with you the number of beta value I have to use, okay? And which is minimum and the maximum. Let me show you one moment. This I took from an old from a talk of mine from this period, okay? So let us discuss in terms of the temperature. Say, what I want to do, I want to study the system, say at T0, where the system is frozen and there are high free energy barriers. The system admits a phase transition where it becomes, for temperature higher than Tc, where it becomes a paramagnetic high temperature system. So in this region, the system is warm and there are no barriers. So let me call, for example, T1 is T0 plus delta. This would be T1. T2 is T0 plus 2 delta, and so on, up to Tm equal T0 plus m delta. So you see, T0 is the temperature, low temperature, where you really want to study your system. The highest temperature must be a temperature really in the high temperature regime, where you don't have barriers anymore. And now we have to understand how much this delta has to be. Then I will discuss with G, but it's very important, but it's less important because we will get rid of it pretty soon. So I will do a point. At low T, the system is typically frozen, high free energy barriers. When the system warms up, the free energy barriers decrease. When T becomes larger than the critical temperature, barriers disappear and the phase space is flat. When the system will cool down again, it will probably explore a different free energy valley, giving us information about a different local mean. So we expect this to work for continuous second order phase transition. I will try to explain eventually why, if the phenomenon of temperature chaos exists. I will define it in the moment. This will kill, and this indeed, I believe, killing us for very high volume. You see, let me try to tell you first, and then I will come back to it. In ordinary statistical mechanics, typically, stable configuration at the value of the temperature are very similar to typical configuration at the nearby value of the temperature. Clearly, in Weiss model, you can have plus or minus, but we already say we don't care about that. In complex Parisi-like system, what can happen is the phenomenon of temperature chaos. That is, it can happen that by changing the temperature of an infinitesimal amount, the microscopical shape of a stable configuration will change of a macroscopic number of spins of order 1. And this we'll see will kill our system like by the way, if you have any question, they are welcome. So this doesn't have to be formal. Okay, so what is a step of simulated tempering? So I will be more precise. Sweep the full lattice, the field variables, spin, gauge fields, S times by running a fixed temperature updating algorithm for the fields at fixed value of beta. In some cases, it can be useful to do it 2 times, 10 times. This can be discussed. Then you propose to the system to change the value of beta. So you say beta goes to a nearby value of beta, or the probability of accepting it would be 0, right? So where m prime equal m plus or minus 1 with probability 1/2. On the boundary of their allowed beta values, you don't care, because indeed you don't care about Boltzmann equilibrium in the beta space. So it's okay, you can go with probability 1/2. So in this case, you compute the variation of the tempering Hamiltonian, that would be, you see, the energy, macroscopic energy of the system doesn't change, but beta changes. So you would have that this factor changes, and then G would change. Okay. So delta H is done like that. And now look up there. As before, if delta H is smaller than 0, you change the value of beta. So you say that the system is going to the new value of beta. If delta H is larger than 0, you accept with metropolis approach with probability e to minus H, minus delta H. I didn't tell you much about how to fix the value of G. Okay. Again, ideal, as we said, would be to fix them to beta times the free energy density, but you cannot do that because you don't know the free energy density, or you already would have solved the problem. So what you will do, for example, at first order, you find that Gm prime minus Gm is minus beta m prime minus beta m times average value of beta m of energy plus average value of beta m of energy divided over 2. This is correct at first order in delta beta. At second order, for example, you add a correction of order delta square that is proportional to the specific heat of the system. So this implies that in large volume, you have to keep delta of order C to minus 1. And here we go. The crucial observation is that after the initial thermalization, that as usual you have to do, at each value of beta, the system is always at equilibrium with respect to the Boltzmann distribution restricted to this value of beta. Even at the moment of beta transition, the system is at thermal equilibrium. I'm very proud of this figure because that was done with our Macintosh of the time. And you see, you recognize it because these were the picture, these were the patterns you could use on this Macintosh, right? So you would always put these patterns in order to color, and you were typically very proud of it. So it was this Macintosh like that. So I got, and I could have redone it, also because you see it's pretty awful the way it is done here. But I am very affectionate, say, to this picture. Also, it's an interesting picture because this picture tells you, see, take the system at temperature T and take the system at temperature T plus delta. If delta is small enough, there is a sizable overlap among the probability distribution of energy at temperature T and the probability distribution of the system at temperature T plus delta. What I mean is that the configuration believed in the styled support here are indeed legitimate bona fide equilibrium configurations both for T and T plus delta. So when you happen to have a configuration here and you propose it to give it the label T plus delta, it will be good for her, meaning nothing bad will be happening. The problem for the choice of delta will be to select this support in such a way that is not too small, that will mean you never accept a change, and not too large, or you're spending time doing nothing. Typically, you do it with Monte Carlo, and what to say, I think I said the opposite of what I wanted to say, but I mean, you understood it. And typically, you do as you do normally with Monte Carlo, that you want an acceptance ratio close to 50%, maybe 30%, or something like that. So you see, this is what I say here. This is what I discussed before. And so, yes, this is the discussion I've already done about legitimate equilibrium, configuration, acceptance ratio close to 0.5. These are figures from the original paper. They seem very naive now, as everything we've done 30 or 40 years ago seems now, but still, right? I show you, you see, this is Monte Carlo time. This is a picture of magnetization in the system with usual Monte Carlo. And so this is random field IC model that was our, say, quite simple model to study it. And this is the evolution of the magnetization, right? At beta equal 0.26 with usual Monte Carlo. There is a state, there is an opposite state that you know, because Hamiltonian is symmetric under inversion of all spins. And you see the system never flips in this, I don't know, 20, 100,000 iteration or what it is. And here I have parallel simulated tempering. And I show you this is with 8 values of beta. And this is, you see, the dynamics of magnetization. You see what's happening. Typically, the system warms up, magnetization easily goes to 0. Then it cools down again because of Monte Carlo, but then with 50% probability, will go in one and in the other. And here, I just selected the configuration at beta equal 0.26. And you see that it's really a continuous, a very large number of flips among the two magnetization. In this approach, the flipping the magnetization is not anymore typically the slowest mode of the dynamics. This is simulated tempering. This is what we proposed. And this, on one side, sits over a large number of development about umbrella sampling, the theory of probability distribution, but also has generated many further developments. The first one being parallel tempering. Indeed, the simulated tempering has been superseded right ahead by parallel tempering, but is very close to what we did, right? It's very similar but important development because it's really easier to implement around. Because basically allows you to eliminate this annoying constant G of M. And how do you do it? You basically allow to the system, you take M copies of the system. And you say that each copy of the system has a temperature B of I, for I going from 1 to M. So you put them at different temperatures. And you don't propose anymore a flip of beta, but just an exchange of beta among two copies. You see, the big advantage here is that the G of M constant will be directly reproduced by this method, by the flipping or not flipping of the method. So again, like before, analysis on numerical results is very easy. This is important because you don't need what is called reconstruction that can be cumbersome, even if later on I will introduce you maybe a method for doing it. So the method. a bit like before, select a discrete set of temperature or inverse temperature values, m of them. T0, the minimum one, is the interesting one. T maximum is a temperature where you are sure you are in the warm phase, but now you clone your system m times. That is, you consider m configuration, C alpha, C alpha of your system, each one at a given value of beta. You start and assign you assign to each configuration a temperature. Then, as before, you do Monte Carlo sweeps. As before, you first do one or more steps of updating metropolis or not metropolis. Well, you can use another method in order to update the field variables. What you want, Swensenbang, hybrid Monte Carlo, what you want. And so you do it at fixed temperature. And when you propose to swap adjacent values of the temperatures for configuration with nearby temperatures. So this is different from what one was doing before. Very similar, but again, in this way, G is not allowed, G is not needed anymore. So delta S now is that, okay, because you are swapping, so it will be what you had before, configuration not prime was at beta, configuration prime was a beta prime, and now you want to sweep, you want to swap. You want to swap the beta, the value of the temperature, so configuration, did I write it? This is simply E prime, right? Sorry, this is beta E prime plus beta prime E, okay? And do it for all configuration couples, C of T1, C of T2, C of T3, etc., etc. Now you have to select T minimum. The interesting one, we'll see that the method is very sensitive to the choice of T minimum. If you go to very low values of the minimum temperature, the methods become more and more slow. T max and the number of temperatures. In a system like that, you have to check, in an algorithm like that, you have to check for thermalization. And this is not very easy. Because again, now the flip of magnetization, that is normally what helps us in deciding if a system is thermalized or not, is not anymore the slowest mode. So you do things like, for example, looking at the symmetry of the distribution probability of the overlap. Yeah, just little thing. In complex system, in Parisi system, the order parameter in the very important quantity is not the magnetization, but is the overlap. What is the overlap? Let me give you a simple definition. You take two systems, two copies of system, say in the same disorder environment, you let them evolve, and you measure with time how these two systems that are independent, but for being in the same disorder, are similar. Their similarity is called overlap. And you can understand that overlap is the crucial quantity. So clearly this overlap will have to be symmetric for an exchange because the Hamiltonian is symmetric. And you can check that the probability distribution in a given sample of the disorder of this overlap has to be symmetric. You can check the convergence of observables, expectation values of different quantities, included correlation function on logarithmic time scales. You can check that acceptance rate for tempering has been kept high. We discussed that before. You can, for example, check that anti-copies of the system will have covered all the space of allowed temperatures with many visits. Okay, a few references. So this is us in 92 and a group of Russians at the same time. This is interesting because again, it shows to you how different communities also were working, and it's very difficult to talk to different communities. For example, that was a journal of chemical physics, and already it was quite far from us and for our background. So we learned about that a bit later. Then there are people in statistics. I mean, Guy Thompson, really statistician, Okay, these are people in polymers, Ukushima and Nemoto, Ukushima, Takayama and Nemoto. And at the end, the results are spectacular. I found that with Giorgio, because we needed that. These are, for example, three-dimension probability distributions of overlap of the system, okay, for two samples, for two separate disorder samples. Please remember that in normal statistical mechanics, you always get distribution probability of observables that are picked in 1 point, okay, maybe 2 with a plus or minus symmetry, with a width that becomes very small when the volume of the system goes to infinity. The pressure, the amount of air that is in this room, in this half of the room, and in this half of the room is really pretty constant, because if the room is big, the probability that you on this side die because there is no air, or suddenly is very, very small, right? Statistical mechanics is concentrated with probability distribution in the infinite volume limit that peak in 1 point. Here, not at all. Meaning, look, for example, I've shown this too, because you see, one thing important in Parisi theory is that you have a part of the probability distribution, you expect them to have zero probability of a zero overlap, while some of them you expect to have a finite probability of a zero overlap. Okay? And as I told you before, the symmetry of these probability distributions is indeed a proof of how well we have thermalized. Okay? And here, for example, you clearly have 3 peaks that are very clear. Okay, and see, for example, you see something coming here, but and it's probably there, this little peak, because it is on the 2 sides. And this, right, the same, you see, you have these double things. And for example, here, okay, you see little peak that you don't see here. So this is somehow the statistical reliability of our simulation. But you see, this shows you that with very high precision, with parallel tempering, you can detect this very complex structure of the probability distribution, of the similarity among different equilibrium systems. These are well thermalized, and these are, see, this is three-dimensional theory, so it's also interesting because you don't have real mathematical proofs yet in 3 dimensions, and this gives you an evidence of how things work. But now there is a little bad news, but I think we have to be honest. We also have to tell the bad news. That is, the system has helped and helps a lot in the volumes we've been able to study till now. But what will it do when the volume of the system becomes very large? In a normal situation, it would be more and more difficult, but in a reasonable way, say power law. But something dramatic would happen. What could happen? This is what I told you before. In usual systems, you change the temperature of a little amount, and the new equilibrium configuration will be very similar to the old. But in some complex system, changing the temperature of an infinitesimal amounts leads to equilibrium configuration that from the microscopic point of view, even if they have similar energy, but they are completely different from the, one at the previous temperature. Energy similar, but the configuration are very different. This makes tempering ineffective. And I feel we are seeing signals of that. Look at this, for example. This is a computation from 2010. It's 13 years now. And there, this is a Janus supercomputer, but all groups that have done that, I think, are the same kind of things. You see, we were able to thermalize a 32 to the cube lattice with a T minimum order of 70% of the critical temperature. All samples were thermalized. And then look at this data to see that when you demand to study the system at a lower temperature, it's more and more difficult to thermalize it. For example, if you really want to thermalize it down to 0.4, so order of 45%, sorry, I don't know, some percent, order 50% of critical temperature, you can only go up to L equal 12, volume of 12 to the cube. Now, even if 2017 precise computation have been done now on simple PC, but in the last years, there have been no dramatic improvements. Maybe we can comment a bit at the end, but the way to understand this kind of failure in progress is probably to connect to this phenomenon of temperature chaos. And also, we are studying temperature chaos, and there are other results that do confirm that. These are just a few references about recent results. This is a 2010 computation that I quoted, and these are the one in which with usual computers we compute things. There is Ilaria Paga, recent PhD thesis that has studied all this question in big detail, and if you want to do a long reading, that would be absolutely perfect for you. And this is it. Okay, I think we are over. We still have 7, but maybe I can go up to 10 minutes. And I will try to tell you a few words about our fantastic business. So meaning, by telling you that I consider smearing as one of the fantastic beasts that I have not discussed, but Maria Paola did it for me, and I'm very grateful. And the idea is always, and this is very much a Giorgio idea, a kind of renormalization group idea, meaning how you can resum things in order to get best possible results. This is what I call here optimal data analysis. And I use the following situation. You have done a numerical simulation at a given value of temperature. You have very precise data. What you can learn from this data? Can you learn something about different temperatures from where you did the simulation? And the answer is yes. And the answer is you can also do a complex values of temperature. And you can do it to cover a region of a temperature that are close to where you are. This can be very important because if you sit close to a phase transition, peaks are shrinking. So in order to cover these peaks, this could be very interesting. And this is a proposal by Giorgio, and then does. I mean, this is visible by Falcioni, myself, Pacello, Parisi, Taglienti. And then, I mean, this is for computing complex singularities. I will tell you why. Then Fehrenberg as well has done the case for using it for the so-called multi-histograms. The original proposal was to study four-dimensional, because one dimension is time, SU2 pure lattice gauge theory. The problem was that when looking at data, also these numerical simulations are really, I mean, a kid game compared to one of nowadays, but this is what we were studying at the time. You get quite small lattice, and people thought that maybe there could be a phase transition. Would have been quite strange to have a phase transition in the pure SU2 theory. And so Giorgio said, we said, let us see if we can look at the complex singularity itself. Because we know how a phase transition works. Partition function in finite volume cannot have zeros on the real beta axis. Zeros can only be for complex value of beta. Phase transition is when these zeros go and pinch the real axis. So if we can look at that, then that would be very interesting. Okay, and also then eventually 1 year later, I used it for computing exponent or for computing the scaling of zeros for the equal 3 Ising model. I will show that to you in a moment. So criticality comes from the zeros of partition function. Lian theory, you need to control values of the complex beta. I've already discussed that a bit. So let me consider a system with discrete energies. So I say the partition function is the sum over all allowed configuration of V2 minus beta H of C, where this sum runs over all allowed configuration to the system. I can rewrite this partition function as the sum over all allowed energy levels of E2 minus beta, the energy of this level, times the number of configurations of this level. This is a way to write the partition function. So let me define the normalized energy distribution function as NW, E2 minus beta W over zeta. And let me notice that clearly this is normalized, right? Because I call normalized and it is normalized. So when I sum over all possible energy values, I find one. Now I can write the number of configuration of a given energy in this way, and I can use two betas to write that. So I say that eta beta, zeta beta, E2 beta W is equal to the same things done at beta prime. Okay, and so let me, okay, this is just a step, but here this means that zeta of beta over zeta of beta prime is the sum over all energy values of eta, E2 minus beta prime. Now you have to imagine that I have numerical simulation done at beta prime, and I can use this formula to derive information about the value beta. So for complex beta, for example, I said beta equal beta r plus I beta I, and at this point, this factor here will give me what? A damping factor that is given by the real parts, and an oscillating factor that is given by the imaginary parts, a damping contribution, E2 minus beta R minus beta prime. Here beta prime is real, so I just have this jumping. And clearly, since these are extensive quantity, this kind of damping is very, very severe. So in order to reduce it, we divide times zeta beta R. This is a bit technical, but I mean, if you are interested, you can look again at the slides and you will understand that, because it's not complicating at all. And so because of this normalization you are reducing the damping factor. And here we go. These are results. For example, this is the paper in which Giorgio and us proposed this method. This is CO2 theory. And you see these are zeros. This is the real part of beta, imaginary part of beta, reconstructing with this method. And the full lines are zeros of the real part. Dashed lines are zero of imaginary part. And you see they cross here. So somehow there is a zero that we find of a partition function at complex values of beta, and then we check that when you go to larger lattice, this zero does not approach the real axis. So somehow this is a direct confirmation by numerical analysis of the fact that you are not building up a phase transition. Also, this is a paper by mine. Here I use this method to analyze the phase transition of a three-dimensional Ising model. So here I compute the imaginary part of the first zero, and you see now this point here is the first zero, this point here is the second zero, okay? And this law, this is versus log n, log of imaginary part versus log n, and this law is connected to the critical exponent. And I want to show that to you because it tells you that you can not only control the first zero in this way. I will take 3 more minutes because I think I have it, because I started 5 past, because I want to tell you a few words about the next subject. This slope is the critical exponent. And so you see, it's amazing. I mean, kind of Li Yang would have been happy because this is really a way to use in a kind of very direct way, Li-Yang ideas to compute phase transition, to analyze phase transition. Okay, these are again and again, you can see here, there are a lot of people from statistical mechanics, from the world of molecular dynamics and so on, and then Fehrenberg and Swedensen, Fehrenberg and Swedensen proposed to use that with a very direct application of what we did for reconstructing data at finite value. And I will close just by a last fantastic beast by Giorgio. Indeed, Giorgio wrote 2 papers about that, and then there was a joint paper. I will quote them. And I tell you which is the problem. Imagine you want to compute a correlation function. This is what Maria Paula has been doing during her talk. Okay, and the problem is you're doing by Monte Carlo. So what you're trying to do is to compute something that is exponentially small when you go to a larger distance by a random method. So you're adding up numbers that are of order 1, and you want to check things, and you want to compute things that are exponentially small. So what does it mean? It means you want to compute some correlation function that does like that, but with a given number of steps, since you are summing numbers that are order 1, you have a noise level. So this is the correlation function, this is the noise level, meaning that after this noise level, this level of C, it will be lost. Can we do something about that? This is what Giovanni with coworkers had somehow initiated. So we need to control correlation function at large distance. Very sadly, this is difficult to do with Monte Carlo. This is what I told you know. And let me tell you which is the idea. I will be very general, okay? This was done for SU2 lattice gauge theory, so Maria Paula framework, but I will be general. So let me say the energy is expressed as a sum of local operators of X, okay? And H is the sum over site of this local operator. That can be sigma I, sigma j, or can be a number of gauge field multiplied in some way, and so on. Now, let me take one copy of the system that is the original copy of the system, and in a second copy, I perturb it, meaning I change the value of beta on a slice of the system. I change the value of beta on a slice of the system. If you think about fluctuation dissipation theory, if you remember the theorem, if you remember about it, you see that this allows us, thanks to computing the response, to computing the correlation function. Maybe I will not have time to do in detail all the development, but the point is, linear response will tell us that you compute directly by computing differences among these two systems, okay, a number that is of order of e to minus xn, or x over xi, depending if you are in field theory or not. So, okay, let me call E0 the unperturbed energy, EK the perturbed energy. So I have the original system, the modified system you see as a delta beta, but I don't want to spend so much time. And when you just do the little computation, you find that the perturbed energy is the original energy minus at order delta beta, basically the connected correlation of energy. So that you have directly. You can do it with different operators and get clearly spin correlation function or what you want. I'm doing it for the energy here. So, for example, you get this. Now the problem is what? That Monte Carlo is not good for doing that, because Monte Carlo gives you yes or no answer. So you don't have a continuity in the trajectory. You need a continuity in the trajectory if you want to kill the statistical noise. In order to do that, use Langevin dynamics. Langevin dynamics, you can hope will be good. Clearly, there is the Lyapunov like exponent, so it will diverge at a given point. But you can hope it will be good because Langevin dynamics is continuous everywhere. So the idea is that you study two Langevin equations, you use the same noise on the computer, and you compute differences. Okay? This is the discretization. You have to be careful. It's very interesting because clearly this is of order of square root of delta t. And this is it. You can use it. So these are the papers by Giorgio, by us. And that was, I said, the paper by Giovanni was an inspiration that Giorgio quotes very clearly in the first paper. No, I think it's important because there are some dates that are very clear, and some dates that have to be clarified better because one discovers more and more that they're very important. Ah, okay. I didn't find it. But already 79 is not so bad. And that's it. So let me conclude. At the end, we were just a remark. At the end of his second paper about, I think, Giorgio writes down, so he thanks Guido Martinelli and Roberto Petronzio, that we all remember with real affection. And say, I'm very happy to thank Guido and Roberto. We have together written the computer program for Monte Carlo simulation, which, with the substitution of only few cards, was used to simulate Langevin equation. And this, Giorgio was not drunk. The problem was really, the computer code was really written by punching cards, right? And when I did my thesis, I punched cards during my thesis. It changed very, I have had only 6 months of punching cards. See, Giorgio more. And so I think it tells a lot, because so much water has been flowing under so many bridges, but indeed so many important results have been obtained by Giorgio and are there to stay, and I think now are there to stay and for all of us to enjoy. Thank you very much.
So thank you very much, Enzo, for the very clear and nice talk. So maybe Giorgio wants to comment and say something about that.
Thank you so much, Enzo, for this wonderful talk. Let me try to see if I remember things correctly, because I believe that we had done a summer Monte Carlo simulation for spin glasses, but at the beginning we were not doing a simulation in the low temperature region, and we were doing up to the critical point, and we were not daring to go below the critical temperature, because we knew that the time would explode extremely large. And I think that at the same time, we were doing some simulation maybe on polymers, on things like that with Giulio Iori, but not for spin glasses. At a certain moment, I think that we were reflecting. I think that we knew that there was a need of some better method to do simulations and to enter in the low energy phase. And at that moment, we devised this simulated tempering algorithm. And only after that, we started, we tried to see, as you show, for easing random magnetic field, and after we did the first simulation in lower temperature.
We did not dare go with glasses in broken phase.
Because we knew that the time would be really very, very large, exponentially large in some parameter. Okay.
Okay, this is completely correct. Yeah, this is completely correct. We had started the simulations and we would sit in one phase. And I mean, I don't know, maybe once we had tried to go down and we were completely stuck. And you're right, with Giulio Iori, we were doing these protein-like object simulations. And somehow we had the same problem of thermalization speed. Indeed, if you look there, for example, the problem was common because Orlandini group, Tesi, Orlandini, etc., was a group studying heteropolymers. I mean, so the exigence was pretty clear. And then we found that, and I remember all the mail of exchange when we started that. It was pretty frantic. I mean, pretty intense. And then it was working. And so when we started to do it. Thank you, George.
Okay, is there any other question, remark? Giovanni?
I am entitled to two questions and one comment.
Yeah.
The first question is, when you are in the temperature chaos, couldn't you simply use the tempering with another parameter that is not chaotic? Because
this is a possibility, but I think we didn't find it. And you see, there is not much, when you take a spin glass object, okay, magnetization doesn't have any sense. You have overlap, and then
you can choose a parameter
because the
that is continuous.
configurations are different.
No, I
I mean,
understand.
you see, the parameter, the energy is continuous.
Yeah.
You have to imagine a spin-like model. Sorry, this is for my friend who work around that. The so-called golf course phase space, right? So you are around. You remember I started by telling the story about annealing, meaning annealing works because deep basins are typically large. This is not always true. So you take a p-spin, you look at phase space, right? So this is free energy. Okay, these are 10 to the 23 dimension. There is a moment, one single little deep. So the problem is that you know nothing about this deep. I tell you why this is a problem that frightens me. Probably something can be fine, but you know really nothing about this configuration. And so this is a very difficult problem. I know, Giorgio, do you think this is correct? What I'm answering?
But you could imagine that you take another intensive parameter like the density, and imagine that in the density there is this continuity that you need.
One should look at this picture and find that there is some graph. Well, if you find that, you're right. Yes, sure.
Okay.
One.
The second point, I'm astonished by the complex temperature, because all the good properties, I mean, it's not more a probability in minus beta h.
No, yes, it's not more. Indeed, there is this fluctuation, but still,
so
it's a function, right? And you can continue analytically function.
No, I agree. But when you sample,
but you don't sample a complex probability. I've been too fast. You only sample at real probability. So beta prime that is real is where you sample, and then you extrapolate.
Becomes a part of the observable.
Yes,
okay,
if you want.
fine.
Okay, so yeah, you can read it like that. So you have data at a real value of a probability. Okay, and then you say, can I extrapolate that? And then you see that you have very damning factors, right?
The freedom in the parameter.
And you put that in the observable. This is the division you do. Correct.
Okay. The third point is that Giorgio came to me with this subtraction.
Yeah.
And
yes.
And offering that. And I say, that's too mysterious to me, so I don't trust. But indeed, you are only partially right. It's not the fluctuation dissipation theorem. It's the unitarity of the evolution operator that permits that is more general.
Yeah.
Whenever the trajectories are correlated, you can demonstrate that the perturbation is not operating on the probability but on the observable. So you have a more general theorem, and on that the distance remains finite. That's
correct. Yes.
Okay.
I simplified, but it's correct. Thank you.
Thanks a lot. One last question. Okay, if not, let's thank Enzo again.